This is ACE lecture about machine learning, and finally we are going to talk about more complex structures like recurrent neural networks, and then we are going to talk about doing machine learning on a cloud using Google Collaboratory. So our theme is today neural networks, recurrent neural networks, and Google Colab. And on the first part of the lecture, we are going to talk about theory of recurrent neural networks, what are these and how to use them. And on Google, on the second part, we are going to talk about more computations, about some tricks and tips, how to train a recurrent neural network. So imagine writing some text by words or by letters, and so after you've written some word, for example Z, you need to write the second one and the third one and so on. And as a human you can do this task very naturally, and let's imagine that a feed-forward neural network which just takes some input and then spews out an output, and imagine this simple, the most simple neural network to compete with this task. So after word there, if feed-forward neural network doesn't know what the context is, it's going to completely fail this task, because it eventually will write the most reasonable or the most probable word after that. So all sentences are going to be the same, and neural network won't understand context and won't understand text at all. So this task for feed-forward neural network is very tough, and of course we can solve it like we can write some words and then tell the feed-forward neural network to tell like the sixth word, knowing the five word behind. But still, it's quite a task, because we can't change an input of neural network, and that's why neural network doesn't have a memory, and it's a very hard task, and it will probably just fail it and output the same and the same sentences. Like it can find some word like the, and then a, and then the, and it will just repeat and repeat this very not bright sentences with just two words, which are the most probable to be. So that's why we need to introduce some kind of memory, and we need to preserve memory and give it to the next neural network. And neural network has an input layer, of course, and it has a hidden layer. Like, you will remember that feed-forward neural network, it has an input layer, a hidden one, and an output. And on this lecture we are going to talk about one of the simplest neural networks is with this structure. We have only input layer and a hidden, or it can be called output layer. So we have just two layers of neurons, and they are connected with weights. And so neural network has an input layer, and input values of neurons, and a hidden one. So it's a natural idea to pass to a new neural network after doing some computations. We can pass previous hidden state or previous input state. So we have some input, and input, for example, is Z. Then it outputs some new word, like apple. Then we store these hidden values, like 0.5, 1, and we pass these hidden values to a new neural network. So this neural network takes input, new input, and new input is going to be like, for example, the same apple. And it takes these hidden values. And then it tries to output a new world. And new word is. And we got some new hidden values. And then we store these hidden values and give it to another neural network. And again, input is like is. Input also consists from previous hidden values, and again we can go on and we output new worlds. So this is how neural network, the simplest recurrent neural network is defined, and it's called just simple RNN, simply. This is abbreviation for recurrent neural network. And we essentially take such neural network, and all these networks has the same table of weights, so some weights W. And we use repeatedly and store this hidden value. And to understand this simple RNN in a more compact form, let's introduce some new mathematical definitions to work with all this flow of data more easily and to write it down in a simple formula. So let's return to a feed-forward neural network. And so on. So we have an input, and it can be represented as a row of numbers or a list in Python. So we are going to call this numbers. There are n of them. We are going to call them a vector. So a vector is a list just of numbers. A list in Python, an input, or a vector. So it's just a list of numbers. And then we have a hidden state. And again we have h1, h2, dot, 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 hm. And it's a vector too. A vector, a hidden vector. And of course we have what defines neural network and its behavior is a table of weights. And we are going to denote it like big W. And table of weights is essentially just a matrix. And a matrix is a table of some values. So it's just a matrix, a table, or a double list in Python, and we're going to call it matrix shortly. So we have this matrix, and we can calculate inputs. We can calculate hidden states using inputs and a given matrix. And in the code, we've done it like that. So we have a list of inputs. And what we are doing is summing x1 multiplied by or like that. And what we are doing is in a code, we are looping whole this matrix and whole this vector like that. We multiply this by that. And if we want to calculate the second hidden state is and so on. So now I'm going to explain what this whole means. So we have a matrix and we have an input. And how do we calculate a hidden state? In a code, you remember that we multiply a row of a matrix by a column, like that. We multiply the first element of the column by the first element of a row, excuse me, on a first element of the column, then the second one on the second one, and so on. And we get the first element of a hidden state. And in Python, we remember that we called it like that. And then if we want to get a second element of a hidden state, we need to multiply the second row by all this column. And we do it like that. We multiply the first element of the second column by the first element of this column. And as a result, we get a new vector. And after applying, then we apply some activation function to this whole vector, and we get our hidden state. And how do we apply activation function? We just apply it elements-wise, or in other words, we apply activation function to this number, and from whole this vector, we get a new vector, like that. We get that. That's how we get a new vector. We element-wise apply this activation function. And whole this table and this formula can be written down in a more compact form, like that hi can be found out by using this formula. We sum over k indexes, so we take a first row and then we multiply it by according x value, and then we sum all of that. And this is the same as that, just written in more compact mass form. And whole this process is called multiplication of a vector on a matrix. And after that, and this is like not the final value of hidden vector. After that, we apply a sigmoid function or some other activation function like that, and we finally get hidden state. And all this process can be written even more completely using just this expression that we apply sigmoid function to a weight matrix multiplied by inputs, just like that. So this expression means that we multiply a vector on a matrix using this algorithm, and we've actually implemented this during creation of feed-forward neural network when we created our whole feed-forward neural network library. So we did the same thing. We had this loop, and you can actually find it and say, oh, that was actually a multiplication of a vector on a matrix. So that's how, using this definition, we can now go on, and understanding recurrent neural networks becomes much easier. Because in essence, multiplication of a vector of a matrix is just taking a vector and creating a new one. And for example, if a matrix is square, which means that number of rows is equal to numbers of columns, then we just actually rotate a vector. And for example, let's take a look at a 2D matrix, which has 2 columns at 2 and 2 rows. And let's multiply it by a 2-value vector. And we will see that we just exchange values, which means that we actually rotate this vector. So, for example, our matrix is and our input is 1 and 0, for example, or 1 minus 1. And then if we want to calculate this product of a matrix on a vector, then we can write it like that and begin multiplication. So first, to get a first element of a vector, we need to multiply this element, 2 by 1 is 2, plus 1 by minus 1 is minus 1. Then we multiply this row by this column, and we get 3 by 1 is 1, by 1 is 3, and minus 1 by minus 1 is 1. And it's actually equal to 1, 4. So we had this vector, and then we get new vector. And then we can, because we have not so many values, we have only 2 values, we can actually draw this vector on a plane and see that such square matrix is just rotating vector in a space. Like we had, this is our coordinate space, and we have a 1 minus 1 vector, which can be drawn like that. 1 minus 1, this is our input vector. And then after applying matrix and multiplicating it, we've got a new one. So you can see that we just rotated a vector, but it only applies if we have a square matrix, and if we have more than 2 or 3 values, we just cannot visualize it because we can only think in 3 dimensions. But usually these vectors in machine learning are quite big, and they can be like even to millions values. So it's very hard to visualize them, but still it's the same formulas can be applied, and the same loops are legible. So that's how matrix and vector multiplication works. And now we can just write down what all this simple RNN is about in one compact formula. RNN consists of input of RNN consists of 2 parts. The first one is actually current input, and the second one is previous hidden state. We take previous hidden state, and by the way, if the hidden if we do recurrent neural network first time, in that case we set hidden state to simply 0, 0. And then we need to calculate new hidden state, ht. And then we have our connections, weights, which can be stored in the matrix W. And finally, we can write this formula. So we take a sigmoid function or an activation, just another activation function from a multiplication of all this input by this matrix. And we just there we just show that we take these 2 inputs together and we concatenate them into one big vector. And then we multiply this vector by this matrix, and we get, and then we apply activation function and get new state, hidden state. And then we can do it repeatedly, and this whole connection can be written like that, without showing all these weights. We can just write that we have this layer, this W, this just layer. We take xt, output new hidden state, and then this hidden state goes here and applies as a previous hidden state. So we have such recurrent connection, and now we can just, for example, if we want to predict a new word, we can consecutively input some words, and then we can use our hidden state and do all this work. And actually hidden state plays a role of a memory cell or some memory vector which tries to not forget what was before and tries to memorize all this context. But unfortunately, simple RNN has a problem, which results that RNN cannot remember a very long dependencies, and it can remember only like up to 10, what happened 10 inputs ago, and it will just forget what was before. That can be explained because if we can write down this recursively hidden state, and like that. So we can recursively define it from the previous hidden state, and then we can recursively define it like previous, and so on. So, however, if values of this matrix are quite low, that in that case, impact of all this of previous and previous hidden layers only slows down and becomes smaller and smaller as we go in the past. So the further we can draw a line of time, and we are here, and the further we go backwards, the less impact of hidden states are. So this hidden state has practically no inputs, no impact, because it was like multiplied by these small values a lot of times, and it was just decreased to a minuscule value. So, like for example, this hidden state is impacted by the previous one by 10%. So, like 90% is 90% impact is responsible for x or input value, and 10% impact is the hidden state is responsible for. And in that case, previous one is responsible accordingly to 1% of impact, and so on. So this impact is becomes smaller and smaller, and this whole problem is called vanishing gradient problem. That's why there was a lot of tries to change this architecture, and one architecture was particularly interesting, and it was a very good tackling this vanishing gradient problem. So we are going now to talk about another more complex structure, but giving better results structure, and it's called LSTM, long-term memory. And it has new implementations, and it's more complex because it has a new definitions like cell state and a gates. So first we are going to talk about cell state. Imagine this LSTM. We are going to write down its a rectangle, and we have input xt, a hidden input, hidden state, previous hidden state, and we also have a cell state, special another vector, which is going to carry all these memories. And this cell state is playing a role of a conveyor belt, and it just helps to take some long dependencies and create long memories and then use them right now. For example, cell state can carry over and over some memories which were created 1,000 iterations ago. And that means that LSTM is natural to thwart vanishing gradient problem, and it's very successful at it. So now we are going to show and look at how LSTM changes all these values and outputs a new one. So the first one, and the LSTM introduces new definition, and it's called gate. So gate, we take a previous hidden state, we take current input, and then we multiplicate them by some matrix, apply sigmoid function, and then we multiply the vector by the cell state, which means that, for example, we had some input, some hidden state, then we get, after applying the sigmoid function, we get we get some values like between 0 and 1, like, and then we multiply it by a cell state. And cell state plays a role of a memory, and that means that we can actually, after multiplying, again we multiply element-wise, which means that we multiply this element on this element on this. We get a new cell state, which is going to be 0, 0, 1. So we changed cell state, and we actually reduced, because sigmoid function is between 0 and 1, we will always reduce a number of memories or information in cell state, because actually a 0 can be called as no information, and the 1 like some important information. So that's why, because cell state only forgets something, this gate is called forget gate. Forget gate. So you can see that a feed-forward neural network has a very simple structure, and now we are talking about LSTM, which has a lot more parameters, because it has a cell state, a forget gate, an input gate, and an output gate, and they're all quite, so whole this LSTM is quite a complex structure. Then after changing cell state, this cell state, a new cell state, travels, and now we need to change cell state or create a new memories. We forget something, and now we need to create new memories. And the gate responsible for this is called input gate, and it consists of two parts, so it's even more complex. First one, we apply a sigmoid function again. So this rectangle with a sigmoid is just a matrix table, and we multiply this vector by some matrix table which is stored Z, and then we apply sigmoid function. That's what this rectangle with a sigma means. And then we create an input vector. It's called an I, and again it's something like that between zeros and ones, and it's responsible for what memories are going to be changed. So 0 is means that this memory won't be changed, and 1 that this memory probably gonna be changed. And then the same input, which consists of previous hidden state and an input, actual input, is squashed between in hyperbolic tangent function. So we have some matrix of weights here. We take this input, this whole big vector, multiply it by some weights, then apply hyperbolic tangent. And as you can remember, hyperbolic tangent lies between +1 and -1. So actually LSTM is going to output values between 1 and -1. And then this input vector is multiplied by new vector created by tangent, and then this whole new vector is added to a cell state. So we've created a memory by adding some new memories. And this gate is called input gate, and it's responsible for creating new memories. So we, to recapture, we forget something, we tell a cell state what to forget using sigmoid function, then we, using sigmoid function, we again tell what to change and what memories to create, then we create here memories, and then we add these memories. And finally, we can write that cell state has changed, and it can be written like a forget vector, which was outputted by sigmoid function here, multiplied by CT and a previous cell state, and plus new memories. So this is forgetted memories, memories that survived forgetting, and then creating a new memories. This is created memories, new memories. And this sign means that we multiply vectors element-wise, element by element. So this conveyor belt changed its value, and now it has a value of C next, CT plus 1. And actually we now need to output a hidden state, and we are going to do it by multiplying, by applying sigmoid function here. Here we are applying tangent function, hyperbolic tangent function. And then we multiply these two vectors and output this as a hidden state. So this whole long journey was just to output hidden state, which was created again by multiplication of, again, some sigmoid function. And this sigmoid function outputs, this whole process is called output gate. Output gate. This is input gate. And now cell state creates some new vector using hyperbolic tangent. And finally, we multiply these values and output something new. So we've got hidden state, and then we can use it again and again recursively for next iterations. So yeah, that's a hard, quite hard architecture, and that's why number of parameters it has increases like in 7 times. So LSTM with the same size as a simple feed-forward neural network is much larger, and it's harder to train on. So now we are going to talk about how to just implement LSTM in Keras, just how to create this model. And on the next lecture, we are going to, on the next part of this lecture, we are going to talk about how to train this network. Okay. So this is mathematical idea. This is how we can enroll recurrent neural network. We've written it like that, recursively, and we can just write it down like a new network passing, an old network passing information to a new one. There we have an implementation of Keras implementation. So if we want to train neural network, a recurrent neural network, we need to define not one number, which is just an input and output values. We need to define 4 numbers. The first one is just a number of output dimension. The second is input dimension, which is just a number of values in an input vector. And then we have time steps and the batch size. So time steps is when we train neural network, we are going to apply this recursively, this whole process. We're going to apply this whole process several times, and this is called time steps. So for example, time steps can be a number of words we are training our network on. For example, we want our neural network to train on, like, write simple sentences, and in that case we don't need to know all this a lot of words, and in that case we can just set time steps, for example, to 20, which means that neural network is going to take 20 inputs, and then it's going to train. We can unroll this, so we are going to create a 20 recurrent networks. And that's why they are going to get 20 inputs. And input dimension is clear, output dimension is clear too. And finally, batch size is size of batches we are taking. Hold this. This is one batch, and if we want to fit neural network, we can take like 50 batches and 30 batches, which makes training more clear and more stabilized. So now we are going to implement LSTM. So that's how all these gates look like. Here we have forget gate, here we have input gate, and here we have output gate. And here we have LSTM. So LSTM doesn't change a lot of parameters, but there we can introduce some new technique for training, which is called dropout. And dropout it prevents a neural network from overfitting by just, if we have some large neural network, then we don't know how many data points we need to feed it, because it can be too large, or if it's too small we can overfit. So in that case we can use technique which is called dropout, which consists in turning off some neurons during training. So we can normally calculate these neurons in training, but with dropout we are going to turn off some neurons with some probability, and this probability is written after. For example, with probability of 1/2, this neuron is going to be turned off, and in this case its value is going to be 0, just 0. And if it's not turned off, then we can calculate its value. So dropout creates a new challenge for a neural network, and now neural network needs to find some way to generalize all this problem and to get good results even without dropout. And of course we turn off dropout if when we want to predict something and actually to do this task. So this technique is used only for training. And here you have useful links for better understanding of LSTMs and a Keras documentation about recurrent neural networks. And I think that's it. Now we have a break, and after that we are going to talk more about fitting neural networks and about fastening these computations.